All right. Our next speaker is Phil Wadler. Phil, I have just found out, also has a fascinating Princeton connection. In the 30s, again, our math department was the best in the world, and Solomon Lefschetz was amongst its many members. One of his students was Albert Tucker. Albert Tucker gave rise to Marin Minsky, who gave rise to Gerald Sussman, who gave rise to Guy Steele, and Guy Steele was one of the co-advisors of Phil Wadler, our next speaker. So Phil Wadler graduated from Carnegie Mellon, and thereafter has taught at a number of institutions, and his research has spanned a very wide range of topics, from theoretical to highly practical in the design of programming languages. So as we saw on our history of the lambda calculus, Phil is well known for his foundational contributions to the development of the Haskell language, and in particular his ideas on how to integrate state into a pure functional programming language like Haskell or the lambda calculus, and his ideas on how to structure programs using type classes. Phil has also had a great impact on the Java language by showing Java how to add polymorphism, which of course it should have had from the beginning, but oh well. Phil helped to correct that mistake. And Phil's also been tremendously interested in the remarkable connections between logic and programming over the years, and he is going to now give us a little explanation of some of those connections between logic and programming.
They told me to come up here and use the screen. I have no idea how to move this forward to the next slide, but we'll find out. There's no keyboard. Oh, there is a keyboard, yay! Right. I want to thank Princeton University and the organizers of the Turing Centennial for putting together the Turing Centennial. It's going to be a marvelous 3 days. I want to thank them for inviting me here, and I want to thank you for staying in the audience. So I'm going to talk about two coincidences involving Alonzo Church, who we've just heard a lot about. Both also involve Turing. And when I was invited here to speak, I was told, well, we'd like you to talk about lambda calculus. So let me say a bit about lambdas. I am very fond of the lambda calculus. I work in the field of functional programming. Here's the Journal of Functional Programming, which I helped found, and you can see we put lambda front and center. That's the pavement in the city of Edinburgh. Edinburgh is well known for its interest in functional programming. And that's the tie that I'm wearing right now. So we're going to discover, right, Turing got scooped by Church. Does that mean that Turing did nothing of value? Absolutely not. But if you look at the value of what Turing did, the key value there was not mathematics, but philosophy. So I tend to think of philosophy as something airy-fairy that's nothing to do with me. But nonetheless, in this talk, I'm going to say a little bit about philosophy. So let me talk about coincidences for a moment. Back when I was in elementary school, they showed us a map. And they said, look at this map, look at the coast of South America, look at the coast of Africa. Oh, look, they kind of fit with each other. What's the reason for that? So we talked about various reasons, and they did indeed mention this idea called continental drift, which said that you start with all the continents bunched together in this one continent called Pangaea, and then they move slowly apart. And that explains why the coastlines look alike. But I'm sorry to tell you this, I'm actually old enough that when I was in elementary school, continental drift was not a well-accepted theory. So we went through all this and we came to the end, and they said, right, so why is it that they look alike? And the answer was, it's a coincidence. Right? Only later did we decide, well, maybe it's not a coincidence, maybe there's something to this continental drift after all. Now, here's a solar eclipse, so that's the moon in front of the sun, and you've got this lovely solar corona that you can see. Why can we see that? Well, it's because the apparent size of the moon from Earth and the apparent size of the sun from Earth are pretty much the same. And so the moon just covers the sun, but you can still see the corona behind it. And it's covering up the sun, so the sun's not blinding you from seeing the corona. This is very fortunate. Why is this? Well, let's see. If we believed in intelligent design, we might say that God put together the solar system that way so that we could see the lovely corona whenever there was a solar eclipse. But if you don't believe in intelligent design, maybe the best you can do is, it's a coincidence. I don't know why this happens, but it's very nice. Lovely and pretty. So I'm going to show you one coincidence that I can explain and one that I don't know how to explain short of referring to intelligent design. Now, one of the kinds of coincidence I'm going to be talking about crops up all the time. So much so that you might say coincidences are no coincidence. Sunspots were discovered by Galileo in 1611, but also discovered by three others. Right? Famously, calculus was written down by Isaac Newton and by Gottfried Leibniz, both in the late 1600s. Joule discovered conservation of energy in 1847, but so did four others, one of them 5 years earlier in 1842. We all think of Charles Darwin in 1859, very famous, published Origin of Species, the theory of natural selection, but actually Darwin had had those ideas for a very long time, and he knew they'd be controversial, so he just sat on them and didn't publish. What pushed him to publish was when somebody handed him a paper by Alfred Russel Wallace, published in 1855, that also described natural selection. And then finally, the telephone, we all know, was invented by Alexander Graham Bell, but actually on the very same day in 1876 that Alexander Graham Bell filed the patent for the telephone, somebody else, Elisha Gray, also filed a patent for a telephone. So you can read a book that says, well, actually, Bell stole it from Gray. You can read another book which says, well, actually, Gray stole it from Bell. And you can read quite a few books that say, well, actually, they both just invented it at the same time. And the reason why all these happen, the reason why coincidences are no coincidence, is you reach a certain point where all the enablers for a discovery are there. And so many people can make the discovery at the same time because they've all seen the same enablers. So it's not really a coincidence that this happens all the time. So let me talk about the first coincidence, the invention of, or rather I should say discovery of, effective computability. So as we already heard about in Dana's talk, you wait, right? Algorithms have been around since Euclid. What do? You wait 2,000 years for a definition of effective computability, and then 3 come along at once. It's just like buses. So we have Alonzo Church's lambda calculus, Stephen Kleeni's recursive functions, Alan Turing's Turing machines, and also, in fact, 4, Emil Post wrote about finite combinatorial processes. So we'll look at this in some more detail. And basically, these were all published in around 1836. 1936. I was only off by 100 years. Thank you for that correction. By the way, if you have any questions during the talk, if I say something that's not clear to you, please raise your hand and we'll try to get a microphone to you and you can ask a question. If I make a stupid error like that, please correct me. On the other hand, if I've left out your favorite bit of history, I've only got an hour, so I'm going to leave some out, or if you want to make some comment, or if you want to argue with me, please save that for at the end. So we'll skip over Dedekind. And let's start with David Hilbert. So we'll leave out all the bits from Aristotle up through Russell and Whitehead. And we'll begin here with David Hilbert. And in 1928, he publishes his books on the foundations of theoretical logic. And one of the things that appears in it is the Entscheidungsproblem. And the idea here is to write an algorithm that will determine, given a sentence in predicate logic, whether or not that sentence is true. Right? So a decision procedure for predicate logic. And he's proposing, of course, we're going to have such a thing. He was very optimistic. And at this point, there is no formal definition of what constitutes an algorithm, what is effective calculability. But that's okay, because they just figured we'll just write one down and we'll look at it and we'll know it's effectively calculable. It's just like art. I don't know how to define it, but when I see it, I know it's art. And he went on with this great optimism, and indeed he gave a famous address at the Society of German Scientists and Physicians in September 1930 in Königsberg, and he concluded it by being very optimistic, saying there's nothing that you can't find out using mathematics, very explicitly repudiating the idea of undecidability, and concluded it famously by saying, we must know, we will know. Wir müssen wissen, wir werden wissen. And here you can see it. It might be a little bit hard to read, but that's it written on his tombstone, which it turns out is quite appropriate. As Robin Gandy, Alan Turing's student, wrote, it is ironically agreeable that the very day before this address was given, a talk was given by this man, Kurt Gödel, presenting the undecidability and incompleteness of logic. So something that's almost baked in to the Entscheidungsproblem is this notion that everything will be either true or false. So given a given proposition, either it will be true and there's a proof it's true, or it will be false and there's a proof it's false. So you could prove everything. And Gödel showed, nope, that's not true. Here is a statement I will show you. And the statement happens to be, this statement is not provable. Okay? And then very similar to the liar's paradox, you work out, well, if it is provable, it must be false. So it's not provable, so it must be true. So there must be something true that's not provable. Right? Very easy. So to do this, he had to show that you could encode into arithmetic the idea, this statement is not provable. So he did this by showing how to assign numbers to every statement in logic, very similar to the encoding that Dana showed you in the previous talk. And then he actually wrote out the first computer program that was a proof checker. And here are the last few steps of it, steps 40 through 46. So by 45, he has these formulas of logic that says x, b, y, and that stands for x is a proof of the formula y. Or rather, the number x denotes a proof, which is a proof of the formula denoted by the number y. And then he says, okay, x is provable if there exists some number y such that y is the number of a proof of the formula denoted by x. And all of these, by the way, are very easy to compute, and you can even put a bound on how long they take to compute. They're what we would now call primitive recursive. Only the last step did you need to look at every possible number. You couldn't put a bound on it. If you looked at every possible proof, you could find one. So that gave you undecidability. And at this point, people began to think, well, maybe the Entscheidungsproblem is not going to be decidable. So these were the initiating circumstances that put it, as Robin Gandy put it, in the air that one might be able to show the Entscheidungsproblem is undecidable. Okay. Well, if we have an algorithm, we can just look at it and say, I know that's an algorithm. Right? Just like you don't need a definition of art to look at it and say, I know that's art. But you might very well want a definition of art if you wanted to be able to look at something and say, that's not art. That doesn't meet the definition. Maybe that is why artists resist any formal definition of what art is. But now, if you wanted to show the Entscheidungsproblem is undecidable, that there is no effective way of computing a solution to a given problem, now maybe you need a rigorous definition of what effective computing means. So that's why, after 2,000 years of algorithms, 3 different definitions came along at once. So here's definition number 1, due to Alonzo Church. If you look on the web, you tend to see 2 pictures of Church. Here they are. I have a fortunate feeling, maybe Dana can tell me about this, that this one's more accurate as to what Church was like. So the thing that you did as a young mathematician, as a young logician, trying to prove your chops in those days, is you came up with your own system of logic. So here was Church's own system of logic. And let's just go here for a moment. Oh, these are the wrong slots. Bugger. Okay. So here, in just 2 paragraphs, he defines the lambda calculus. There it is in print, the very first lambda expression. There's the very first application. And just in 2 paragraphs, he can give the complete definition of lambda calculus, including bound and free variables. Now, as I said, he was interested in doing this as a logic, and I'll explain more about that in just a moment. But even then, he had an inkling that there might be more to this, because he actually says right near the introduction of the paper, there may indeed be other applications of the system than its use as a logic. Prophetic words. So here's our lambda calculus in the way he wrote it out. There are just 3 constructs, right? It's like Beck's beer, only 4 ingredients, lambda calculus, just 3 constructs. Variables, abstractions, application. And we tend to write them almost the same way now. And Dana Scott has already taken you through this, so I won't go through it in detail. But I will point out that the reason he wanted it for his logic was to have a very uniform notion of variable binding. So whereas we would normally do quantification by saying for all x, some formula A holds, what he would do is he'd make up a function. The formula A is a function of x, and then he would pass that function in to a constant for all, and that's the way he would express quantification. So he had this very nice way of doing quantification in terms of lambda expressions. So, as Dana mentioned, it was eventually discovered that that particular system of logic fell prey to paradoxes in much the same way as Russell's paradox. So they had to give up on this logic based on lambda calculus, but by then they had the notion that maybe there was something to these lambda expressions. And by then they had the notion, which Dana explained to you, that you could encode numbers as lambda expressions. And so Church put forward Church's thesis, which said, here is the definition of effective computability. Take a given lambda term, give it as argument another lambda term denoting a number n. Take that lambda term and via the substitution operation, reduce it to its normal form. That will be another numeral encoded as a Church numeral in this form. So you take your number, encode it as a lambda term. You've got this other lambda term, which denotes your function. You apply that to the number, you reduce it, you get another number. So we now have functions from numbers to numbers encoded as a lambda term. And now he could use, so he said, that is the definition of effective calculability. And then using that as the definition of effective calculability, he could pose a problem that did not have an effectively calculable solution. It was to determine if a given lambda term would loop forever. And shortly after that, he published a second paper using the same techniques to show that the Entscheidungsproblem is indeed undecidable. So many mathematicians breathed a sigh of relief because they realized that doing mathematics couldn't be automated. There was no given effective procedure that could determine the truth of every statement in a given logic. Okay, well, now let's look at Stephen Kleene. He was one of Church's students. And as Dana mentioned, it was very easy with lambda calculus to see how you represent numbers, how you represent addition, how you represent multiplication, how you represent exponentiation, how you represent adding 1 to everything. Everything was easy except one thing, subtracting 1 from a number. And one day, as he mentioned, Kleene was at the dentist. He doesn't elaborate whether he was nervous or happy or under laughing gas or whatever. But he came up with this idea that Dana described a bit about a way of computing the predecessor function. So Dana showed you how to do it with pairs. That works if you're counting from 0. Back in these days, they counted from 1. So counting from 1, you needed triples. That was similar to the technique that Dana showed you. And so when he was done at the dentist, he went back and brought this result to Church. And it was sort of just in time, because Church, in fact, they had this idea that maybe you could do quite a lot with lambda calculus. But at this point, Church was ready to give up. He said, I can't figure out any way of defining this predecessor. Not surprising, because it was a bit tricky. So maybe we better give up on this lambda calculus. So just in time, Kleene worked out how to do predecessor, and shortly after that they decided, right, we can do everything. This is the definition of effective calculability. So they went to Godel and they said, look, this is the definition of effective calculability. And Godel reacted exactly the same way that modern developers do when you show them a functional programming language. He said, not on your life. Right? I do not believe that this corresponds to effective calculability. So Church very reasonably said, all right, you tell me what you think effective calculability is, and I will show you that that's equivalent to lambda definability. Well, Godel wasn't sure he could do this, but indeed, in a series of lectures given at Princeton, he talked about this idea of a general recursive function. So Godel talked about this in lectures at Princeton, and it was based on a note that had been sent to Godel by Herbrand. So Kleene took this definition, wrote it out in great detail, and proved indeed that it was equivalent to lambda calculus. And then Church went back to Godel and said, look, see, your definition and my definition are equivalent. And Godel said, maybe my definition was wrong. So this sets the stage for Alan Turing. So Turing was a young student at Cambridge. Max Newman had introduced him to these undecidability results of Gödel that we described, again setting the stage. All you need is some definition of effective computability, and then you could show that the Entscheidungsproblem was undecidable. And laying in the field at Grantchester, the idea came to Turing. The idea of the Turing machine, and then he wrote his paper saying, right, I'm going to show you a machine. And very interesting, early on he says, in sections 9 and 10, I give some arguments with the intention of showing that the computable numbers, that is, the numbers computable by a Turing machine, include all numbers which could naturally be regarded as computable. So in other words, anything that a person sitting down with pencil and paper, following a given procedure could do, could be done by a Turing machine. And he gave philosophical arguments to this effect. And then he's very concrete about it, right? He says, in particular, I show that certain large classes of numbers are computable. They include, for instance, the real parts of all algebraic numbers, the real parts of the zeros of the Bessel functions, the numbers pi, e, and etc. So you did not find Church talking about computing the real parts of the zeros of the Bessel functions. Right? That was Turing's very practical bent. And then he goes on, the computable numbers do not, however, include all definable numbers, and an example is given of a definable number which is not computable. In other words, there are problems that you can specify well, such as the Entscheidungsproblem or the halting problem, that cannot be decided by a Turing machine. And here's his very first example of a Turing machine. He was interested in real numbers, so he was interested in sequences of integers. So here, this infinite sequences. So this computes the infinite sequence 0, 1, 0, 1, 0, 1, and so on forever. It has 4 states. His very next example, which I won't show you, computed the sequence 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 1, and so on, so counting up. And then he did more complicated things, right? All done in this very concrete style. Now, I mentioned these sections 9 and 10. Robin Gandy, Turing's student, went back and looked at these later, right? And this is the point about philosophy, right? Turing made an argument that anything a human being could do could be done by a Turing machine, a human being following some set given procedure. And basically, Turing had certain assumptions that the human being had to write down their working, that the working would be in a series of cells, that you could put those series of cells in a row if you wanted to, that there's a fixed upper bound to the number of symbols that could be written in a cell, right? You can't write an infinite number of different symbols in a finite space. That at each step we're going to just alter one symbol at a time, one symbol per cell. There's a fixed upper bound to the distance that you could move between each step of the computation. So you couldn't look infinitely far down the tape, only finitely far. And there's a fixed upper bound to the number of states of mind of the computor. The computor, ending in OR, not ER, being the person doing the computation. So Gandy, looking back on this philosophical argument, said, well, actually, if you look at that, that's as rigorous as most mathematical proofs. So what Turing really did is he sort of axiomatized what you could expect a person to do and then proved that a Turing machine could do what you could expect a person to do. But instead, we just view this these days not as a mathematical theorem, but as philosophy, as the explanation of why a Turing machine ought to be able to compute anything that is computable. And this then, when Gödel saw it, he said, okay, I believe that's computable. Okay. Now, Turing, of course, was scooped by Church, and he found out about that. And they did consider saying, there's no point in publishing the paper. But they decided, well, maybe there's something here that's new and useful, as indeed there was. And so they did go ahead and publish it. And indeed, the first version of the paper included a sketch of the proof that Turing machines and lambda definability were equivalent. And then, as you heard, Turing went off to Princeton to work with Church. And he wrote a paper giving in great detail the proof that lambda definability and Turing machines are equivalent. And he actually wrote out a Turing program that was basically the first computer program that could evaluate lambda expressions. And I have great fondness for the introduction to this paper because he says, okay, so this provides a justification of Church's calculus if you believe in Turing machines, or justifies Turing machines if you believe in lambda definability, but also it allows the Turing machines, which generate computable functions, to be replaced by the more convenient lambda definitions. So there you go. You have it from Turing. Functional programming is the way to go. I'll skip over that. Then the last point is email post. So we heard about post systems, but this was before post systems. Right? You might say, right, this idea of a machine with a tape and states, that's unique to Turing. No. Post wrote this paper, also published in 1936, inspired by the work of Church and Kleene, but knowing nothing of Turing's work, where he says, let's consider an infinite sequence of boxes. So he didn't call it a tape. He just called it a sequence of boxes. And each box, he didn't allow a finite number of symbols in each box. He only allowed two. Either the box is marked or it's unmarked. So you could argue that this was even more elegant than what Turing did, though perhaps less practical. And then the operations you could do that the worker could do, he talked about a worker rather than a machine, and the worker is given a sequence of instructions, and the instructions must be one of 5 forms. Mark the box the worker is in, so the worker is assumed to be looking at one box at a time. He can mark it, he can erase the mark in a box, he can look at the box on his right, he can look at the box on his left, or he could determine whether the box he's in is or is not marked. And you just have a sequence of instructions, and each of these said what the next instruction to go to is. And for this one, there was a choice of 2 instructions based on whether it was marked or not marked. Looks very much like a modern instruction set for a computer. So in fact, Post came up independently with the idea of Turing machines. So does that mean that we're wrong in giving all the credit to Turing? Should we perhaps be dividing the credit with Post? Or even give Post more of the credit? Because I think if you read this, anybody who read it would agree it was more concise and more elegant than a Turing machine. Well, no. Okay? First of all, Post didn't prove anything. He just gave this definition and said, I think this is equivalent to lambda definability. But he didn't prove it. But much more importantly, Post didn't have the philosophy. He didn't argue anything that any person could do can be done by this machine. So it was the philosophy that was Turing's important contribution, as well as, of course, many of the practical aspects. Okay, that concludes my discussion of the first coincidence. Let me now move on and tell you a bit about the second coincidence. This is something that goes by the name of Curry-Howard, or propositions as types. So again, I'm going to tell you a story about various people doing similar things at the same time. So here's Gerhard Gentzen. And he came up in 1935 with natural deduction. So there were many, many systems of logic, but Gentzen had this wonderful insight that the rules of logic should come in pairs, which was a wonderful idea that has served us well to this day. I'll show you a bit about that in a moment. So this is copied from Gentzen's original paper. Oh, and by the way, for many years they'd been using upside down E to mean there exists, but Gentzen decided on, in the same paper, on using upside down A to mean for all. And indeed, this paper introduces the two systems of logic that are most widely used to this day, natural deduction and sequent calculus. But I won't say very much about sequent calculus. Let me stick with natural deduction. So here it is, the way Gensen wrote down, and here are the two rules for implication introduction and elimination. Here are the two rules for and introduction and elimination. And here's the way you would see those written in a modern text. And they are absolutely identical, symbol for symbol, to what Gensen wrote down. We have not changed Gensen's notation. The only thing we changed was that he wrote it with German letters, and we write it with English letters. So the key insight here is that things come in pairs. So how do you know how do you know you have a proof of A and B? You know it if you have a proof of A and a proof of B. So if you have a proof of A and a proof of B, you can conclude that the formula A and B holds. So that's and introduction. Let's say you have a proof of A and B in your hand. What can you do with it? Two things. You can conclude A, you can conclude B. So that's called and elimination. So the rules come in pairs, rules that introduce the connective and rules that eliminate the connective. Similarly for implication. So implication was interesting. It said if assuming A, you can prove B, then you know A implies B. That's introduction. And elimination says, and notice this little X superscript here, right? When you introduce this, you have to say which assumption you're discharging. And the other rule, elimination, says, let's say you have a proof that A implies B. And let's say you have a proof of A, then you may conclude B. Right? Back in the Middle Ages, they called this modus ponens. So from a proof that A implies B and a proof of A, you may conclude B. Now, he wanted to show the logic was consistent. In other words, he wanted to show there was no proof of false. So I'm going to show you the modern version of this that wasn't discovered till many years later by Pravitz in the 60s. But the idea is, let's say you've got some proof where there's an introduction rule followed by an elimination rule. Then that means we're going to introduce A implies B, and then somewhere else we have a proof of A, and we'll eliminate that and get B. Well, wait a minute. We don't need this intermediate formula in here. We can get rid of this intermediate formula. How do we do that? Well, this said, from the assumption that A is true, let's prove B. But look, I've got a proof of A right here. So I'm not going to assume A. I will just copy in the proof of A that I had. And now copy over the rest of this proof that I've proved B directly without ever proving A implies B. So I've simplified the proof by getting rid of this intermediate formula. Notice the proof is not necessarily smaller. It might be much bigger. Why is that? Because this assumption here might be used many, many times. And we're going to copy this proof once for each time the assumption is used. So it gets bigger, but simpler. Similarly here, from a proof of A and a proof of B, I can prove A and B. If I do elimination, I've got A. Hey, let's just use the proof of A directly. So this time it really is getting smaller. This is good because it shows that if you have a proof, you can always simplify it to get rid of any intermediate formulas that don't appear either as an assumption or in the conclusion. So this was very good because he said, if there's a proof of false, it will only involve subformulas of false. That is, formulas that appear within the formula false. False is pretty small, right? It doesn't have any subformulas. It's sort of like, what part of no don't you understand? Okay? So using this, he could then show that the logic was consistent, that there were no proofs of false. It was just easy by looking at the rules and knowing that he only needed to look at rules involving subformulas of false, and there weren't any. Okay, so here's a typical proof. This is a very silly proof. It's the proof that from B and A, I can conclude A and B. Order doesn't matter. Well, how would I do that? assume B and A. From B and A, I can, of course, conclude A by eliminating the second, by retaining the second component. And of course, from B and A, I can prove B by using the other elimination rule. Oh, now I've got a proof of A and a proof of B, so I've got a proof of A and B, and I discharge the assumption, and there's a proof that from B and A, I can conclude A and B. And just to show you how simplification works, I will run through this rather quickly. So here is that same proof copied, and here is a proof of B and A just from the assumptions B and A directly. So this is a very roundabout proof. Can we simplify it? Let's see. Here's an introduction. Here's an elimination. We could reduce that by copying this proof where those two assumptions are. So we'll copy it. And there it is simpler. Oh, and look, in the process of copying, this and I moved on top of that and E. So I've got introduction followed by elimination. I can simplify those. Hey, presto! Here's a much simpler proof that from these two assumptions I can get A and B just directly. So we can simplify proofs. Isn't that lovely? Okay, keep that in mind. Let's go back to Alonzo Church. Remember, he wanted lambda calculus for a system of logic, but the system of logic was proved inconsistent. Rats. But maybe by overlaying a type system on top of the logic, it could be made consistent. So let's introduce type systems. Now, he didn't write the types in quite this notation, but I'm going to use this notation. So let's see. Let's say x is a free variable of type A, and using x I build up a term n of type B. Then lambda xn is a function with an argument of type A and a result of type B. Let's say L is a lambda term that denotes a function from A to B, and say M is a lambda term of type A. That if we take the function, this wants an argument of type A. Here is something of type A, so we can apply the function L to the argument M, and the result of that will be, what is it? Oh, it's a function from A to B, so the result will, of course, be a B. And you can also do pairs. Now, Church didn't do pairs directly. He did them by encoding. But you could also have rules for pairs. So if M is a term of type A and N is a term of type B, then Mn is a pair whose type will write A and B. And then given a pair, you can extract either its left component or its right component, which will indicate by subscripting with 0 and 1. So again, we want to evaluate our programs, right? So how do you evaluate the lambda term, lambda xn applied to M? Answer, take x and everywhere x appears, replace it by M. So n with M replacing each occurrence of x. Does this preserve types? Well, let's check. N has type B on the assumption that x has type A. M has type A. We'll replace every occurrence of x by M, which has the same type, so the typing is preserved. Similarly, how would I reduce a pair? So I build up a pair, N has type A, N has type B. Mn is a pair of type A and B. I select out the left component of that, so that will just be M. But we know that M must have type A because it did when we proved the pair Mn had type A and B. So types are preserved. What you might want to know, in order to get a proof of the consistency of the logic, is that this process of reduction always terminates. And indeed it does. And it turns out, published proofs didn't appear till much later. But it turns out the first proof, unpublished, was done by Alan Turing. So Turing had a lot to do with this type lambda calculus. And, so here's the program here's the simplest program I could think of. Given a pair Z of type B and A, select out the right component and the left component and pair them together and return that. So this takes a B-A pair and returns an A-B pair. Just swaps around the two things. Let's try to apply that function. So here I've built, let's say y has type B and x has type A. So yx is a B and A pair. I can take this function and apply it to it. So I'll take yx and substitute it everywhere for z. So I do that. Of course, now I've got, here are the two z's. Each has been replaced by yx. Now I've got a pair, so I can select out the left and right components, and I get x and y. Okay, I would like you to all now reach into the seat pocket in front of you. You will have been supplied with a pair of rose-colored glasses. Please put on your rose-colored glasses. When you look at the world through, when you look at this program through rose-colored glasses, what do you see? Well, because they're rose-colored, of course, they will eliminate all the red parts. You will just see the blue parts. And you'll see that. Easy as pie. It's very simple to see that simply typed lambda calculus and intuitionistic natural deduction are easily seen to be clearly in one-to-one correspondence. Furthermore, it doesn't just work for the two connectives I showed you, it works for everything. So conjunction becomes products, pairs. Disjunction becomes sums, choices of things. False becomes the empty type, the type with no values in it. And of course, implication becomes functions. And this was written out for combinatory logic by Haskell Curry, and actually written out for lambda calculus and intuitionistic natural deduction by William Howard. He first wrote it down in 1969, but didn't actually publish it until 1980 in the Curry-Festschrift. So this obvious correspondence is called the Curry-Howard correspondence. So propositions correspond to types, proofs correspond to programs, and normalization of proofs corresponds to evaluation of programs. But there's more. It's very robust. It's not just natural deduction and typed lambda calculus. It's also type schemes and the ML type system, which means that the logician Hindley and the computer scientist Robin Milner discovered the same thing a few years apart. It's also Syst and F in logic and polymorphic lambda calculus, which means that the logician Girard and the computer scientist John Reynolds discovered the same thing a few years apart. It means that monads, which, as was mentioned, can be used to model state and exceptions in pure functional languages, written down by the category theorist Kleisele around 1965. You could go earlier. Maji came up with the computational applications in 1987, but these correspond to modal logic, written down by Lewis in 1910. And it goes on. I won't go through all of them. So what is the legacy of this? The legacy is many, many different functional programming languages. I won't name them all. And I'll skip over that bit. But the other legacy, right, proofs we saw can be represented as lambda terms. So if you want a computer program that can do type checking, just the way that Godel did in his first paper on undecidability, a great way to represent a proof is as a lambda term. And this idea has been used time and time again, first used by De Bruyn in the automath system, by Mertenloff in type theory in 1975, and many, many systems, often used at industrial strength now. You have proofs of entire compilers and of entire chip designs and of entire operating systems, all done in this style. I'm going to skip over that one as well. And I will round this off by going back to philosophy. Let's say we want to talk to aliens. We've actually tried to do this. Okay, so this is a plaque on the side of the Voyager satellite. This actually shows the solar system. There's Earth. There's the a schematized version of Voyager and the path that follows going out of the solar system. So we're trying to explain to aliens what this is. So there's Sol. The lines have a length corresponding to the distance to various pulsars. They have marks on them which are in binary the frequency at which the pulsar goes. Now, I predict that if aliens found this, they could probably work out, all right, length of the line corresponds to distance. They would understand what binary means, right? You could work that out. They would understand what frequency means, and they could work out, that's where Earth is. Then they have to decide if they want to go there. So then they look at this bit. So there's a picture of the Voyager in the background, so you can see how big people are. Now, this bit, I'm sure they would understand. This bit, well, depends. Say Star Trek is right. Then they will look at this and they'll say, wow, they look just like us. Except they don't have pubic hair. But possibly, right, aliens, if they do, if Star Trek is wrong, and it really is Life Gym, but not as we know it, they might look at this and go, no idea what that means. So they might look at this and say, hey, let's go there, right? They might look at this and say, tasty, let's go eat them all up. Or they might just not understand this bit. So in 1996, when I had just started at Bell Labs, a movie came out called Independence Day. And it's sort of a remake of War of the Worlds. And the aliens come to Earth and they blow up big buildings like the Empire State Building. This is 1996. This is when blowing up big buildings in New York was fantasy. And how do they destroy the aliens? So in War of the Worlds, right, the aliens were destroyed by a bug, a virus. So how would you destroy them in a film made in 1996? With a computer virus. And what language do you write the computer virus in? Java. Right? Java spread through the known universe. It must be Java. So actually, this was back in 1996 when I saw the film and I saw this on the screen. This is actually a shot from the screen of the movie. I looked, I thought, it's C! I just started at Bell Labs. Brian Kernahan and Ken Thompson and all were just down the corridor from me. I thought, wow, these guys made it into popular culture. Isn't this great? Of course, it's a weird dialect of C or Java because it only has open braces. So this kind of seems unlikely, right? Would aliens really have come up with object-oriented programming and C and Java? That seems to involve an awful lot of arbitrary choices. I think the chances of that happening are less than the chances of looking at pictures of people and saying, oh, that's people. Right? Doesn't seem very likely that they would get C or Java. What about lambda calculus? Just 3 constructs. Corresponds to intuitionistic natural deduction. So we'll hear a lot about universal machines, right? But I think maybe lambda calculus might claim to be, in a different sense, a universal programming language. Wait a minute. I'm not sure I want to say that. Because now we're used to the idea of multiverses. So this is the ad for a play called Constellations. It has in it the most brilliant stage direction I've ever seen. Normally you see pages and pages and pages written in italics say, the stage is this, there's a door on the left, there's a window in the middle, there's a door over there, people will enter here, and so on. This has only one stage direction. An indented rule stands for a change of universe. Right? So the idea of multiverses, that every time you make a decision, well, you're like Schrodinger's cat, and the decision could go either way. And there are different quantum universes in which it goes either way. So there are there are an infinite number, say, of different quantum universes. So look at all those infinite different quantum universes. Some of them might have different gravitational constants. Some of them might have other laws of physics that are different. Now, you might have a better imagination than me. But for myself, I cannot imagine one of these quantum universes. where logic does not hold, where you do not have the rule of modus ponens, where you do not have natural deduction, and therefore where you do not have lambda calculus. So I do not want to call lambda calculus the universal programming language. And the reason I do not want to call lambda calculus the universal programming language is because calling it universal is too limiting. Thank you very much, and I would like to remind you that when you have a tough job to do, that means that this is a job for lambda calculus.
All right, so I've seen that shirt once before. It's hard to follow that up with questions, but perhaps question over here.
I love the way you told the story of the events of the various notions of effective computability. I just want to add a couple of quick footnotes. One is you are very much on target when you mentioned Post not having a philosophy, and Post would have been the first to agree with you. He really had all the technical ideas way back in 1921 in terms of things like what were later called rewriting systems. And the thing that stopped him was exactly not having such a philosophy. And when he wrote to Godel, trying to explain to him what his earlier ideas had been and what he was missing, he says explicitly, something like what Turing did were exactly, exactly the words he used. The other...
Sorry, those words were used by Godel or by Post?
By Post. The other is that I think you were just a little unfair to Godel in the story. He was a very cautious man and always cautious about everything, including the gases coming out of his refrigerator. And but in those lectures, in the notes at least for the lectures, I couldn't get Kleene to be sure about how much of it was in the actual oral part of it. He has he not only has this Herbrand Godel thing, which Kleene based his work on, but also has a footnote where he introduces primitive recursive functions. Of course, he's still just calling them recursive functions, but what we call primitive recursive functions. And he says in the footnote that it's very likely that if all recursions are included in this, that everything effectively calculable will be included. So he really knew it. He was just cautious. In fact, I wrote him when I was preparing an anthology of papers in the 1960s and says, weren't you really stating Church's thesis at that point? And he wrote back and said, no, I wasn't, because I wasn't really sure until Kleene's paper that my specific formulation of recursion was really all-encompassing.
Calculus is that it involves unary complexity notations, such it takes you exponential time to get up to a polynomial length number. Is there as unique and salient a system for dealing with trees and ways that give complexity as we know it?
Absolutely, yes. Any data structure can be easily encoded in lambda calculus. I just showed you Church's original encoding, but you could easily encode binary numbers instead of unary. You can easily encode any kind of data structure. And indeed, Dana Scott showed you part of that with pairs and lists.
Okay.
But
So,
arbitrary trees are very easy to encode in lambda calculus.
right, but there are multiple ways to do it, and they're all a little bit complicated. Is there one that's unique and salient and as compelling?
Yes, the one I use. It's natural enough that if you sent a lambda term encoded in that way to aliens, I think they could decode it, right? They wouldn't necessarily come up with the same one, but they'd be able to understand it. It's not arbitrary.
Dear Lambda Man, up and away. I wanted to say about the Entscheidungsproblem. There were decision methods earlier than Hilbert Ackermann. Bernays and Post worked on the propositional calculus very early on, and Schroeder and Lervenheim had worked on monadic predicate calculus. So there was a concept of doing decision problems, and it was just a question of expanding them to the full thing. So there was more behind.
Oh, absolutely. I had to skip over an awful lot of the history, only some of which I know.
Well, from what was said over here, it looks like this is the proper thing to have in here, that Turing was a bit reserved, so we have lots of these signs here. It seems that one of the things that happened until Edgar Dijkstra made his short letter was that people were afraid of Turing's proof in the same way that physicists are afraid of perpetual motion machines. And that he said if you structure your programs in certain ways, they're not absolutely general, but now you can do more with proofs, and that's what everybody was waiting for. So it wasn't, certainly Turing's work was perfectly general, but there was a practical problem that I think came up, that sometimes people worry about things that they didn't need to worry about.
So one thing I've often wondered actually is, right, Turing did this brilliant philosophical job with the Turing machine. And so people got used to thinking of computing as being an imperative sort of thing. They didn't think of it in the functional style that Church had done it. I really wonder sort of if Turing hadn't been quite so good at inventing the Turing machine, and if he had followed up on this comment saying, you know, it's actually better to write these programs down as lambda terms. If he had done that early on, maybe we'd be much further ahead with building reliable, robust, efficient, easy to build software, because functional programming would have taken off much earlier. So that's my bit from the functional programming camp.
I'd like to thank our speakers for a great first session. Thanks very much.
Thank you.